Hello students, welcome back. Let's go back to section 2. I believe I completed everything here except for one problem, which is arguably the most important, especially in terms of exam preparation. This is very typical in terms of technique, but also it has a great standalone property. This kind of function is called linear fractional function because we have a linear function in the numerator and also linear function in the denominator. It is so important that it has a certain name attached to it. It is called Möbius function, named after German mathematician Möbius. The same Möbius associated to Möbius band or Möbius strip, like this. This gentleman here. Of course, I'm not going to go too detailed into Möbius band or Möbius function or projective geometry, those kind of things. I'm going to focus upon the technique here, and that is very, very relevant for our level. Okay, here we go. Step 1 is, of course, switch x and y. Let me expand the font a little bit. We have a lot of fractions here. X is 3y plus 2 over 2x minus 5. And we are looking for y. Once you get it, then we have the inverse function. So how do you solve for y? Oh, excuse me, a typo here. I did not completely switch x and y. Okay, we have it here. 3y plus 2 over 2y minus 5. Okay, all right. Let's solve for y. Now, please note that this is a linear equation of y. And how do you solve a linear equation? Step 1, denominators. Step 2, parentheses. Step 3, like terms. The same process that I've been emphasizing from chapter 1 all the way back to chapter 1. The three-step process. Parentheses number 1, oh, excuse me, no. Denominators number 1, parentheses number 2, and the like terms number 3. Okay, we have denominator, so let's remove the denominator. Multiply 2y minus 5 to each term. This is what you're going to get. And please do not forget this parentheses. I've seen so many students missing parentheses like this and then screwing things up from here. Whenever we have big horizontal bar, hidden parentheses are always present. This one. This, okay, all right. So multiply the denominator to both sides. We got this multiplication. In the right-hand side, we lost the denominator. Okay, step 1 is done. Denominator gone. Step 2, parentheses. Break apart 2xy minus 5x equals 2, 3y plus 2. Did I do this right? Okay, all right. Parentheses gone. Now what? Like terms. But what are the like terms here? Remember, we are solving for y, so y terms are like terms. Here is a y term, and here is another y term. These are like terms. So what do? We want to take the like terms together, so get all the y terms in one side, everything else to the other side. Remember this trick because we're going to be using it over and over again, and also we do this in calculus as well. So 2xy, that's in right place. Flip the 3y to the other side. And then 5x, flip it over to the other side. And that's what you get. Remember? Here we have y term here. Everything else is moved to the right. Okay? Y terms on the left-hand side, everything else to the other side. And then what? What do? We take the like terms together. So let's take them together. What do you mean by that? Factor y out. Now, this equation looks very benign. Previously, solving for y, it looked intimidating because, well, number one, there are two characters, yeah, of course, but even more importantly, there were two y's here. Even here, it was intimidating. We have to get y, but there are two y's. How do you get that? Move all the y terms on one side. We got improvement here, okay? All the y's on the left-hand side, everything else on the right-hand side. So we have an improvement because all the y's on one side, but still, we still have two y's. Now, after factoring it out, we only have one y, and that's why we did all this. That's why removing the denominator, that was pretty much a straightforward thing to do. Why did it break up the parentheses? Why did it take all the y terms on one side? Here is the reason. We wanted to factor y out. Now it's pretty simple. Divide out this 2x minus 3 to the other side, and you're going to get y equals to 5x plus 2 divided by 2x minus 3 and that is my inverse function. Of course, the denominator should not be equal to 0, so I would like to add this condition as well. That's going to complete the problem. This gives us the domain, everything other than 3/2, and this one here is the inverse function. Let's have a recap. Switch x and y, that's the starting point of all these inverse function problems, and then solve for y, okay. How do I do that? There are two y's, one upstairs, one downstairs. Forget about that for the moment, and let's follow the procedure. Denominator is number 1, parentheses number 2, like terms number 3. Denominator, okay, let's remove it. Straightforward. Break off the parentheses. So far, nothing spectacular took place. From now on, something spectacular. Get all the y terms on one side, everything else to the other side. If you have something residual in the left-hand side, no, it's not going to work. Only y terms should be in the left-hand side. If I have some y terms in the right-hand side, it's not going to work either. All the y terms in one side, everything else to the other side, and then we can factor it. Once I have this factorization, it's easy. Flip this 2x minus 3 to the other side by dividing out, we have the solution. Now, what is the probability you're going to see this kind of problem in the exam? More than half. Yeah, more than half. So this is a highly probable problem. Let's go to the answer key here. All right, switch x and y and solve for y. The same deal. So far so good. Get all the y's on one side, everything else to the other side. Factor y out and divide. We get the inverse function. How about the domain? Denominator should not be equal to 0. So x is not equal to 3/2. And that will give me the domain of the inverse function like this. Everything is okay except 3/2. How about the graph? Here, blue is the original, red is the inverse function, and please note the symmetry. Symmetry with respect to the principal diagonal. X goes to y, y comes back to x. That's why we are getting this symmetry with respect to the diagonal. Okay, that'll do it. That concludes lesson 11.